Is that better? Yeah. Talking anchorage laps of reinforcing steel, what I'm aiming to do is to describe the change in the rules from the 2004 to the new version of EC2. I want to try and explain the rationale for these, and at the end of the talk, to quantify the impact that the changes will have on the anchorage and lap lengths that will now be required in construction. Before dealing with the codes, though, I would like just to remind you about some features of bond behavior. And firstly, that when we're talking about bond, there is not just a single mode of failure. When we get bond, we're pulling a bar out of the concrete. Compression struts are set up, which radiate from the bar, as shown in green. And that creates a ring tension around the bar. And if that ring tension is overcome, we will get a splitting failure, and the bond failure will occur by the concrete spalling off as the ribs bear on the concrete. So that form of splitting failure is a very brittle form of splitting failure. Certainly if there is no confining reinforcement present, it can be very brittle indeed. The other form of failure, which occurs if we have got a thicker cover, and hence a greater capacity in the ring tension, is that the bar shears the concrete over the top of the ribs, the concrete doesn't split, and the bar pulls out, leaving a relatively smooth bore. And while that failure mode cannot be described as ductile, it's non-ductile. You still get a reduction. You don't get much by way of a plateau there. The other aspect that I want to mention is that when we're designing to codes, we have got very used to the idea that bond is an average over the bond length, an average stress. But of course, there is quite a variation in the bond strength as you go through the lap length. So you can do a simple analysis. This is just a linear elastic analysis. And you see the distribution of bond stress through the lap length that you get. And you can see that it's very much emphasized towards the ends of the lap with quite a low stress near the middle. That's based on a linear elastic analysis, as I say, so it does tend to exaggerate the position quite a lot, but nonetheless, it is an effect that is there. And so we do need to take account of the non-linearity in bond over anchorage and lap lengths. So the principal sources for the revision, well, if I go back to where 2004 version came from, it was essentially based on the CEBFIP model code in 1978. There was another edition of that model code in 1990, but there was very little change. So if you think about that, that was a code published in 78. That would have included research up to, let's say, about 73, 74, 75. And so that means that really the existing rules in 2004 version of EC2 are something like 50 years old. That's a long way back. The first British code to introduce rules for anchorage of deformed bars was in 72. We're going back a long way there. The main sources of information for the revision, therefore, in 2023 was firstly an FIB bulletin, 72. That contains a lot of the technical background that was represented in the model code of 2010. Since then, a lot more work has been done to develop the design rules, in particular in connection with the reliability analysis that has been used to formulate the design rules. So to move firstly to anchorage lengths of straight bars, the 2004 version had a three-step process to calculate the bond length LBD, the anchorage length. First of all, you calculated a basic bond strength, which was dependent on the bar size, on the casting position. Then you got a notional anchorage length, which was subsequently modified to take account of cover in excess of a minimum, of hooks and bends, of the contribution of confining reinforcement in the form of links or stirrups, and hooks and transverse compression, let's say. These influencing parameters were all multiplicative. So they were all factors which combined and therefore compounded the effect of each individual one. Now that didn't seem terribly rational, so things have changed. Simplified provisions. This is what now appears at first in the 2023 version. You no longer have a set of equations. We're going directly to anchorage length without going through two intermediate steps. You have a lookup table, in which you enter with the characteristic concrete strength, the bar diameter, and you just look that up and you get a bond length in terms of a multiple of bar diameter, bar size. They are simplified in the extent that they work for a constrained set of circumstances. So they're limited to rib bars of not more than 32 millimeter diameter, or intended bars up to 14 millimeter diameter. They are based on a minimum cover of 1.5 times the bar diameter, which need not always be applied, of course, and they assume the full design strength of a grade 500 bar. So they are a bit constrained, but they are intended to cover the vast majority of circumstances with a moderate or a modest degree of conservatism. So they're quick, it's quick and easy to use. The values in this table are, as you might expect, based on a somewhat more detailed set of provisions, which was equation 11.3 in the revised version. You have a series of factors there. KLB is a coefficient, which will normally have the value of 50. You've got a casting position factor. You've got the bar diameter there. You have an expression to take account of the stress that's being developed, or the design stress of the reinforcement that you're using. You've got an expression for the concrete strength, for the bar size, and for the cover ratio, the ratio of the cover to the diameter of the bar. Cover CD, cover dimension CD, depends on the spacing and the minimum of cover, both laterally and vertically. A top limit of 3.75 diameters is used for CD. That is partly because of a limit of experimental evidence, and also partly that this really represents the transition between the two modes of bond failure that I mentioned earlier, between the splitting and the pull-out mode of failure. The next line just represents the limit on bar size. You're basically going down to the factor on bar size only goes down to 12 millimeter diameter. And that is both empirically based, but probably because when we're looking at the deformation patterns of the small bar diameters, the rib area that's required for a small bar diameter is less than it is for the larger sizes above 12 mil. Concrete strength, again, is limited to effectively a characteristic strength of about 83 MPa. If you happen to have if you want to look at more detail, again, you can use you can substitute CD conf in space instead of CD, the cover dimension. And CD conf allows for the contribution of transverse reinforcement or confining reinforcement, and it also allows for the contribution of transverse compression, delta CD. And again, limits are set there, which correspond to the transition between splitting and pull-out failure. Probably transverse reinforcement, you would have to have really very dense amounts of transverse reinforcement to get much benefit, but transverse compression is highly beneficial to bond. Importantly, these confined parameters are all summative. So this fits much better with a physical model. Although the expression 11.3 is derived from a semi-empirical analysis, it seems the basis of that analysis can be justified much better by a summative rather than a multiplicative combination. The expression, the design expression, is derived from a mean strength expression, which was proposed in the FIB model code and in Bulletin 72. And of particular interest is the non-linearity in the stress developed with increasing bond length. And we've had to introduce this. This is one of the reasons why there is no longer a bond strength in the code. Because if you take the trend shown by equation 3, by the solid green line there, you can see that the bar stress does not increase in proportion to bond length. It increases at a reduced rate. And so what you see is if you go to the different grades of steel there, the bond strength, the bond stress in these is shown by the gradient of the dashed and dotted lines. And that gradient varies with whatever grade of steel you're using. So we do need to move away from bond stress for that reason, in addition to simplifying the method of calculation. So what you now find is that you get bond length, the anchorage length increases at an increasing rate as the design strength of the bar increases. The influence of concrete strength, well, EC2, the 2004 version, had bond strength varied with concrete strength with an index of 0.67. And that was valid for short bond lengths of maybe 5 diameters or so, where it is just the tensile strength of the concrete that goes around that resisting the ring tension. But if you start to look at longer bond lengths, then you have to consider the bond slip relationship as well. And with the higher grade concrete, the bond slip modulus is much stiffer, so you get a bond stress that peaks much more at the ends. And failure is obviously going to be initiated by what happens at the ends of, in this case, a lap or at the anchorage. So that means that the 0.67 overestimates the influence of concrete strength. You've still got the tensile strength of concrete being important, but it is moderated somewhat by the bond slip stiffness. So that justifies the reduction to an index of 0.5. Bar size, well, EC2, there was a bar size effect, but it only applies to bars in excess of 30 millimeters, 32 mil. Now we have got a factor which goes from 12 millimeters up to 50 millimeter as the maximum. That compares the value of the function that if you actually get there. But if we base that instead on a 32 millimeter diameter bar, just to get the relative effect of these two approaches, then we find that above 32 millimeters, it's more or less what it was before. But when you come down to the smaller sizes, you now get a factor of less than 1, and therefore it allows you to reduce the anchorage length relative to the 32 millimeter. So we've got both increases and decreases now in this version, in the latest version. Just to briefly show the influence of transverse compression, again, compared to what there was in the 2004 version, we have got a much greater influence of transverse compression. And this is mainly because we've now rebased this to splitting failure, whereas formerly it was derived from a pull-out failure. And so when you get a given transverse compression acting on the anchorage, then first of all, it suppresses the splitting failure mode and pushes you towards a pull-out failure mode. And hence, over that interval, it is much more effective in allowing a reduction in the anchorage length. Casting position, again, there's a change here. The coefficient in the 2004 version was 1.0 on bond for good conditions and 0.7 for poor conditions. So that effectively is a 43% greater anchorage length from the poor condition. That has now reduced to 1.2, although if you were dealing with bentonite, a rather specialist application, mainly concerned with piling, then it remains at about 1.4. There is a small difference in the depth of concrete where I've assumed a good condition, but by and large, there's not a huge difference in the outcome there, just a difference in the presentation. To justify this, as I said, there was a lot of data has been accumulated over the 50 years or so since Model Code 78 was derived. And if you look at a lot of the test work that was carried out early on, tests that were carried out on short bond lengths, you can see that there is, in some cases, a markedly high top cast ratio, by which I mean the ratio, the strength of bars cast near the top of the pore could have been, in some cases, as low as 20% of the bars cast near the bottom. But this is true only for very short bond lengths. The minimum anchorage length is 10 bar diameters. So really, the left-hand set of dots in that slide are really of no relevance for practical construction. As the bond length ratio is increased, then we're seeing an increase in the top cast ratio, or at least the bottom end of the top cast ratio. And again, this can be partly explained by the difference in the local, in the distribution of bond stress through a lap, because here you've got the local bond slip model from Model Code 2010. The blue line shows from the elastic analysis the distribution of bond stress for good conditions. The red dashed line shows what you get for poor conditions. And obviously the poor conditions, you have a much more uniform distribution of bond strengths through the lap length. So that offsets the increase in strength that you get from the higher grade concrete, or from the casting for the bottom cast bars, I should say. And this is borne out by analysis of the test data, that we actually get bond top cast ratio reducing, approaching 1. If you look at data from laps, you actually find that, yeah, you're up about, for practical bond lengths, you're probably up about very close to a factor of 1.0. So with a little bit of conservatism in there, it's been moved to the factor of 1.2, which I think is probably still fairly conservative. End hooks and bends, well, it was entirely irrational in the 2004 version, in that with a straight bar, as cover increased, you can see in the right-hand graph, you were able to reduce the bond length. But not if there was a hook in the end. Not necessarily if there was a hook in the end. So that really seemed illogical. It was also illogical to increase the contribution of the hook with an increase in the strength of the bar. The contribution of the hook would be limited by the bearing capacity of the concrete, and to therefore increase that based solely on an increase in strength of the rebar was illogical. So the revision now gives you a fixed reduction. The hook or bend, or standard hook or bend, is taken as a 15 bar diameter reduction. It's slightly more for U-loops at 20 bar diameters. To move to tension laps now, after anchorages, EC2 in 2004, a factor was applied to lap length depending on the percentage of bars lapped relative to the total cross-sectional area. Otherwise, rules were fairly similar to those for anchorages. That's now come down to a factor of 1.2 for reasons that I'll explain. It's a little bit surprising, to be honest, that we have a factor of 1.2 here, because most of the calibration for the design expression was carried out on laps. Now, it's true that when the design expressions were tested against data, that the lap length, there was a lower average ratio of design strength to measured strength, a lower ratio of measured to design strength for laps than for anchorages. But nonetheless, that would seem to be an argument for reducing the factor on anchorages rather than for increasing the factor on laps, given that the calibration had been carried out on laps. The reason for that really is not so much for a full design strength, but it is more to do with the scatter in results for bond lengths less than that required to fully anchor the bar. So quite why we have this situation, quite why that all arose, is a little bit difficult to understand without further detailed investigation. It may be a systemic factor attributable to rounding of indexes relative to the mean strength expression, or to the change between a characteristic value being used in the design expression as opposed to a mean strength being used in the expression it was derived from. But it's a little uncertain, in my view, in that area. Clarification, there's been some clarification of the bar spacing dimensions for staggered laps, just with a change in the diagram. But again, I'm coming back to the fact that we have got a big change, big improvement in our understanding over the period. In 1975, what was favored was a hydraulic pressure analogy for laps versus anchorages. So the bursting force generated by bond action in an anchorage was seen to be like a hydraulic pressure on the outside of the bar, so that in an anchorage, you get one force, a certain force radiating out from the bar in all directions. In a lap, you get the force, double the force perpendicular to the plane, and the same force parallel to the plane. However, that has been extensively negated by bond tests, by tests that have subsequently been carried out. So the factor that was in the 2004 version is quite inconsistent with test results. Robustness has been mentioned in other contexts, quite important for laps. You may allow the support moment to be redistributed by up to 30%. If you do that, that basically means that you're starting to yield the bar at the serviceability limit state under working loads. And as I mentioned earlier, failure, a splitting mode of failure can be extremely explosive, can be, the slide on the right just shows what happens as the beam fails and you've got concrete cover flying off in all directions. So obviously the first step is to locate laps away from area of high bar stress wherever possible, but an additional set of requirements have been introduced where the lap is in the vicinity of a potential plastic hinge or yield line. And you've either got to provide additional confining reinforcement, which makes failure a bit less brittle, or you've got to limit the area of bars that are lapped, or you've got to design for 20% above the normal design strength for the steel. Compression laps, well, 2004 version made virtually no allowance for anything with compression laps, presumably because of a lack of evidence at the time. Now, the end bearing of a compression lap, the end bearing of a lap, can provide a substantial amount of resistance and basically equivalent to that provided by the end hook or bend. Strength of compression laps, you can see that as we come down to a bond length of 0, there is still a significant intercept on the bar stress axis. The only thing is that the bar stress detailing is quite critical because you get both high bond and a concentrated bearing at the ends of a lap, a compression lap, then it is very important to include links close to the end of the lap, as is shown there. You can't obviously make use of the end bearing if the bars terminate close to a face, otherwise you're just going to get a pop out of concrete there, and you can't make use of the end bearing there. There's a little bit of new concrete, new content, post-installed reinforcing steel, usually epoxied in. The rules are broadly consistent with those for cast-in structures, but obviously there's additional requirements there as far as the anchorage mortar is concerned. The cover, although that increase in cover requirements is more to do with installation than with resistance once the bar is grounded in. And there's some additional restrictions on other things. Headed bars are now in there as well. If you're using these as stud for example, punching shear reinforcement, you've got a lot of concrete round about it. Side cover, in effect, is then more or less infinite. There are simplified rules. Basically, you can just use the yield strength of the bar. There are detailed provisions for head capacity if you're wanting to use the head in combination with a straight length of bar. But you can't just add the two peak values together. There's a 10% reduction, which allows for the fact that these two mechanisms will not reach their full contribution simultaneously. The expressions, 11.3 and such like, have been extensively validated against data. Test data, there's over 800 results for tension laps, nothing like as many for compression laps, but you can see here that only one of the tension lap tests, of the 800 tension lap tests, fell below the line of equality. For compression laps, they are 2 below the line of equality, but these did not comply with the detailing provisions in the code. So to look at the impact on design, the final section, I've just taken a fairly simple beam section to look at what effect these changes are going to have compared to the 2004 version. But in doing that, I want to also make due allowance for the change in bar strength over that period. Because when these rules were first formulated, we were looking at a bar strength of around about 400, a grade 400 bar, roughly speaking. Let's say at that case, you had a bond length corresponding to 40 bar diameters. We take now yield strength, the characteristic yield strength goes up to 500. The provisions in the 2004 edition imply that that should be 50 bar diameters. You should go up to 50 bar diameters, 25% increase. But if you allow for the non-linearity that's now involved in the latest in the revision, you should be looking at not a 50%, not a 50 bar diameter lap, but a 56 diameter lap. If you looked at the Model Code 2020 version, it would suggest a 20% increase above what you have with EC2. So in making these comparisons, I've included 3 versions. First one in red, the design bond length according to the current version of the code. The next one, making allowance for the increase that should have come in because of the non-linearity. And finally, the version in the draft, the 2023 draft version. And this is the position for anchorage of straight bars in a good casting position. And you can see that with the dark blue case, the larger bar diameters do show an increase. The smaller diameters, 12 mil, there is no significant increase. If we look at poor casting position, well, because we've reduced the effective casting position, there is generally little increase or, in fact, a significant reduction. Hooked or bent bars, yeah, the contribution, particularly for the larger diameters, is very significant. You can reduce the anchorage length where you have got a hook or a bend on the end. And similarly for transverse compression, the allowance for transverse compression is now greater. For laps, yeah, generally slightly shorter. For compression laps, much shorter, because we now take account of the end bearing. And so to summarize, there's been extensive revision of this section. Bond strength has been eliminated. There's a non-linear variation in resistance and capacity with bond length, and bond lengths are now calculated directly. There's a lookup table for routine situations subject to some limitations. Hooks and bends now, they are more effective for larger bars. Compression laps and anchorage as well. Again, you've got a gain because we're taking account of the end bearing contribution, and there's some new content in there. So typically, there's a modest increase in the design anchorage length as a result of the changes, but generally there are reductions. There are generally a neutral effect or some reductions for bends, hooks, bends, U-loops, or for bars and compression. Thank you for your attention.